So first of all, I would like to thank the organizer to giving me the opportunity to talk here, and to Katie for the nice introduction on photoevaporation, so I can jump into the topic here. I would like to try to address this sort of simple question, which is, can X-ray photoevaporation explain all the transition disks that we can observe, or which fraction of them? And so this is sort of the overview of my talk. I will talk briefly about transition disk demographics, and what we can see, what are the transition disks that we can observe. And then I will talk about the photoevaporation models and the new models of X-ray or XUV photoevaporation that we developed in Munich within this framework on this research network focused on transition disks. And then I will talk about how this affect the disk evolution and some conclusions related to this. Okay, so I will go briefly into transition disk demographics. So what are transition disks? Transition disks were defined observation in 1989, and where this disk where there's a flux in the near infrared, which is consistent with the inner gap, right? In the gap in the inner parts of the disk. And this now has been solved with the recent imaging by Halma and other facilities here. In this is an example. We can see this transition disk with the inner gap, right? And what is the fraction of these disks? So this seems rare, this transition disk, following this paper by Muzzarolo et al. 2010. They are roughly 1% around 1 mega-year-old circumstellar disks, and they are roughly 10% around 3 mega-year-old systems. You can see this from two different perspectives, right? You can see this as this is a very short phase in the disk evolution, and so that's why only 10% of the system are seen in this phase. Or you can see that as only specific configuration of the system, right? If you have a couple of giant planets in the inner system, then they can carve this deep gap in the inner part of the disk, and that's why we have such a small fraction of this, because it's difficult to form a system of giant planets in the inner part of the solar system, of the planetary system. I will show this plot a couple of times, so it's better if you look at it carefully. This is taken from a review on transition disk done by Barbara and Ilaria Pascucci in 2017, and it shows basically all the known here. The color dots are all the known transition disks, mainly from SEDs, where we have here the accretion rate onto the central star as a function of the whole of the transition disk. Right? And we can see here, overplotted in gray, some of the models coming from photoevaporation that we had. So the initial idea was that we can divide this plot in two parts, right? We have the system with small gaps, with small holes and relatively small accretion rates that can be explained by photoevaporation from the central star. And when we are going to larger holes and larger accretion rates, the only way we can explain those systems is to dynamically sculpt it from system of giant planets or from a binary companion. And so we wanted to address these problems and many other things about photoevaporation. We started, I will show a picture of how photoevaporation operates, and then I will show all the new models we did. So this has already been explained, but you have a process in the disk. I will remain agnostic on that. The transport angular momentum outwards and mass inwards, and this goes down with time, while at the same time the star is irradiating the outer part of the disk and generating a thermal wind, up to the point where this photoevaporative winds is coming, or this mass loss rate due to photoevaporative winds become larger than the accretion rate onto the central star, and so you start carving up a hole here, roughly the gravitational radius, as Christina was telling you. So you have the inner disk accreting onto the star on a viscous timescale, and then the stellar radiation can directly eat the bulk of the disk in the outer parts and rapidly disperse the outer disk, right? So as Christina showed, we have different profiles here. In the literature, there have been developed a series of models focusing only on EUV or on FUV, or like the models that James Owen developed, and I'll follow up on this line here. A disk irradiated by EUV and X-ray spectra. And as Katie was also telling you, these profiles are quite different, especially as order of magnitude. The mass loss rate coming from X-ray or FUVs on the order of 10 to the minus 8, while it's roughly 2 orders of magnitude less from the EUV. So I developed this framework here where we are using sort of Pluto, which is a grid, a Eulerian grid hydrodynamical code, coupled with moccasing with this ionization code from Barbara Colano in order to have a relative transfer hydro simulation. And from this simulation, basically, we get sort of the streamlines of our photoevaporative wind and at the sort of an equilibrium state, at which point we sort of integrate the streamlines of our wind, and we obtain some surface density as a function of radius, surface density mass loss rate as a function of radius coming from our photoevaporative winds. Then we can use this to apply them to 1D viscous evolution code and coming up with these demographics that we can compare with the plot I've shown you before, or we can post-process these results with, again, with the relative transfer code to obtain synthetic lamp profiles and that we can quantitatively compare with the line observations. This is an example of one of these simulations. This is done for a 0.7 solar mass star, in this case, X-ray luminosity of 210 to the 30 x per second, where we have, I was showing you here the density, the temperature, and the radial velocities, and I've plotted here the streamlines of this photoevaporative wind. I think this is a line every 5% of the cumulative mass loss rate. So this is done for primordial disk for several X-ray luminosities, and now we're expanding it also for several stellar masses. And this has been done also for transition disk. In this case, we also see an example of a transition disk where we self-consistently obtain the inner structure of the disk with the flows curved in the inner part and then leaving radially like with this thermal wind, like a Parker wind. What we obtain here is a sort of a cumulative mass loss rate of our photoevaporative wind as a function of the X-ray luminosity, for example. Yeah, I'm always comparing with this James Owen model because this is in a sort of, we improved this model by James Owen. I can go into that if you want. So basically, we had a temperature prescription, which is also a function of the column density, which was not present in the James Owen models. And we see that basically we got a sort of a factor 2 to 3 high accretion mass loss rate due to the photoevaporative wind, the X-ray plus UV photoevaporative wind. And we saw also with respect to James Owen that we reach a sort of maximum, a plateau for X-ray luminosity up to which basically there's no increase in the X-ray luminosity, doesn't change the mass loss rate due to photoevaporative winds. And this is mainly because at this point here, with this very high X-ray luminosity, X-ray radiation, basically there's a sharp transition between the disk temperature and already a temperature of 10 to the 4 Kelvin, like basically the UV irradiation. And basically at this point, the stellar radiation can't possibly remove more mass because it reaches all the mass until the point where all the X-ray radiation is absorbed. And what we obtain as well, basically, is, as I was showing to you, deriving this surface mass loss rate of the wind as a function of radius, right? We can then apply this directly to 1D viscous evolution codes in order to understand what is the evolution of the disk. And this is what this is an example where I'm comparing my models in green with the James Owen old prescription, and also in this case in UV prescription coming I think from Katie Clark's old models. And we see here the evolution is a function of age, and we see that in this model for this specific case we have the disk is dispersed on a time scale of between 2 and 3 megayears. Then this is old James Owen model, and then the UV is able in this case to remove the disk on a much lower timescale because this is a factor 2 order of magnitude lower in the mass loss rate due to the wind. Then we can basically take this, run a series of these models like this one here, spanning the parameter space, and we can then generate the probability of finding the system in a specific configuration. So with a certain, as well, again, as I was showing here, with a certain hole of the gap and a certain accretion rate onto the star. So this was the old James Owen model. This is our new model, where we can see that we can explain basically gaps up to 30, 40, 30 AU basically, and so a much larger fraction of the observed transition disks. not all. There's still this part here of the graph which is populated by larger holes and larger accretion rates, which we can't yet model with only using photoevaporation. But still, we expanded much more this region here. Another point I wanted to make is that we are also with the student modeling now carbon depleted disks. It has been shown that the disks in the outer parts are carbon depleted, possibly due to freeze out of the carbon onto grains that are then settling on the midplane, and so this atmosphere is depleted in carbon and oxygen, possibly, and the carbon is one of the main opacity contributor to the X-ray radiation. And what we obtain in this is a preliminary result, but we can push our mass loss rate by again a factor 3 or 4 with respect to solar metallicities, and we can explain a larger area in this plot here as well. But now we are still working on doing a series of these runs for different carbon depletion factors, and in order to get more realistic study. This is a work in progress. Okay, so I would conclude with some of this what I would have said. So basically, we have this scenario here, and we are pushing a little bit this region, this transition, the first class of transition disk formed by photoevaporation in our models towards larger hole and higher accretion rate, slightly higher accretion rate onto the central star, and trying to explain it more and more. So there's a large shaded regions here of transition disk, which can be explained both by a dynamically sculpted system or by direct photoevaporation from the central star. Of course, we are still using quite a simplistic modeling of our system. There have been also in the last years, a series of papers by Goodman and Goodman, and also by Nakatani et al., which were trying to model, as also Katie was mentioning, we're trying to model everything self-consistently, so chemistry, relative transfer, and hydro all at the same time. And we are trying to tackle also this problem and try to see what are the differences in our modeling and why we obtain different results. And so with the help of Tommaso Grassi, we are also including Chrome into Pluto in order to include some microphysics into our models. And also we are trying to address what are the different contributions of these different ingredients, as well as Svenning was talking about what is the role of the MHD winds and how MHD winds and photoevaporative winds can interact. In our group also there's a person working on this, and it would be very interesting to understand this role better. And finally, in this population synthesis model that I've shown to you, we are considering only the gas, while the role of the dust dynamics is important, especially because transition disks are observed through dust, and so we are looking into that as well. And with that, I'm ready to take questions. Thank you.
Go back 3 slides to
which slide?
17. Yes, I guess the one before this one. Yes, so that's an update, right, on James' work.
Yeah,
James had a figure like that too, and I asked James before, so I ask you now: how is the probability calculated?
Yeah, so we run 1,000 of this 1D viscous evolution simulations, right? And then we basically check at each time what is the gap size and the accretion to the center star in each of these simulations, right? And then we calculate over the total lifetime of the disk of all the simulation, what is the probability of this one of these to have a specific gap radius and accretion rate into the central star, right? So on 1,000 realizations and looking at the time evolution of the disk, we calculate the probability of looking at one system with that specific configuration.
The way that I understood that plot by James was that the probability was the probability that you could explain the transition disk by being due to evaporation.
Yeah. By photoevaporation, only by the photoevaporation. Yeah.
And the dots that are not there are probably carved by other things,
Yeah.
like planets.
Yeah, like planets, for example, both in the outer and the inner part, actually, because I don't know, especially these points here, these are inside the gravitational radius, and so basically also these inner points here, we can't really explain them by photoevaporation, right? So both these points here and also these outer points here, we can't really explain them by photoevaporation, right? Yeah.
What's the simplest way to understand the fact that you're pushing out by a factor of a few in radius based on how you've revised the Owen et al. Thermal descriptions?
Yeah, so we can, so basically we are able to open a gap at several locations in the disks, right? So looking at this plot here, this is an important plot, right? We are looking at the solid line here, which is coming from our work. We have a peak here around the gravitational radius, but also we have sort of an increased mass loss rate here around 10 to 20 AU, and this is because sort of in some of these simulations opening up at around 20 AU in our disk evolution, and this was not observed in James
I'm
knowledge.
just wondering what's causing that difference at about 20 AU, say.
Yeah, okay. I do not have a real physical explanation. We are looking to try to understand that here, but this is coming from the simulation.
Could you say something about how well we think we know what the stellar accretion rate should be once you've opened up a cavity in these transition disks? Is that a well predicted quantity, or
Once you open a cavity?
Well, so in those plots you've got you've got predictions there for what the m dot should be.
Yeah, yeah. So it depends. I mean, depends how early you open a gap in the disk, right? If you're able to open a gap quite early in the disk evolution, depending also on the disk mass, then you can have still a very high accretion rate onto your central star. So it depends. So since we were able to push this the mass loss rate to the wind by a factor 2 to 3 higher than the old James Owen models, then it means that we can open a gap earlier in the disk evolution, and so we are also we will have higher mass accretion rate into the center star at the time of gap opening. This is the main idea, right? Then yeah, yes, yeah. This is the only thing I can say.